Hi, everyone. Welcome, and thank you for joining today's webinar. My name is Sakshi Sethi. I'm with OSA's Corporate Membership Program, also known as OIDA. Really excited to introduce today's webinar. It's sponsored by one of our corporate members, OptiWave. But before we get started, I'm just going to take a minute to review a couple of housekeeping items. If you need any assistance during today's presentation, you can use the chat icon. It's located at the bottom of your screen. That's the best way to get in touch with me during the webinar in case you have any technical issues connecting to the audio, video, the video feed that you're receiving, or if you have any technical questions for me, again, please use the chat box. The question and answer for the speaker will be happening through the Q&A icon. It's also located at the bottom of your screen. This is going to be your predominant feature that you're going to want to keep your eye on. In case you have any questions in the webinar, I suggest you ask them in real time. Our speaker will do his best to get to all of the questions at the end of his presentation. You'll just click on the Q&A box, a pop-up window will appear, you'll type in your question directly and hit submit. And then finally, this is just a reminder, today's webinar is being recorded. So in case you're not able to stay for the full hour or you really enjoyed this and you want to be able to forward it on to a colleague, I recommend checking back on the event website by the end of the week or first thing next week for the recording. And that will be available publicly so you can go back and rewatch the video. And that's everything that I have. So without further ado, I'll go ahead and pass things over to our speaker, Scott Newman. He's with OptiWave, and he will get us started.
Thank you for that. I'm just getting my presentation up here. There we go. Bring the Q&A up. Sorry, all of the Zoom forms closed on me when I started sharing my screen. There we are. So thank you everybody for joining today. My name is Scott Newman. I'm the lead researcher and product manager for the OptiFDTD product that is carried by OptiWave. And what we're going to do today is we're going to take a look at the designing of photonic crystals within that environment. So before I do get into that, I do want to talk about polarization. So in a lot of references, papers, even textbooks sometimes, they'll make references to transverse electric or transverse magnetic, and they don't specify the actual field components they're talking about when they do that. And the problem with that is sometimes somebody refers to TE, but that actually more corresponds to the TM that you're looking at. So this is one of the problems when you're comparing sources. So that's something I want to talk about here. And fundamentally what it comes down to is transverse to what? So obviously it's transverse magnetic, transverse electric, but what are these transverse to? And it comes down to the definition of the plane of incidence and also the alignment of that coordinate system to the structure you're working on. So I have two examples here to highlight that, just to hammer the point home. The first one is what most people are exposed to when they start using looking in photonic crystal research, and that's the text by Giannopoulos et al. Called Molding the Flow of Light. They set their coordinate system to have an infinite Z, and then the photonic crystal is described across the X and Y axes. The transverse is taken to be the axes that are transverse to the infinite direction. So what that means is their transverse electric has EX and EY, and therefore HZ, and their transverse magnetic has HX, HY, and correspondingly EZ. The OptiFDTD product follows the standard set forth by most waveguiding references. An example of this would be Okamoto's Fundamentals of Optical Waveguides. So the coordinate system for us is set with infinite Y, and propagation is along the Z. The crystal is in the XY direction. And we base our polarization and the definition of transverse such that there is no field that is in the direction of propagation. So for example, transverse electric cannot have any electric field in Z. Therefore, we have HX, HZ, and EY. And in TM, we have EX, EZ, and HY. And this actually corresponds, when you look at the results, the TE in the molding the flow of light standard actually matches TM in our standard. So sometimes people will run simulations or look at results and try and compare it to a reference and say the TE and TM are switched. And it's just a standard difference. That's all. It's not no issue with the calculations. Different people have different standards of what transverse actually means. So the structure we're going to be focusing on today is your standard hexagonal lattice. This shown here is with a defect in the center. So when we talk about photonic crystals, there's three things that you use to describe the crystal. One is the lattice that you're using. In this case, it's the hexagonal one. Then there is the lattice constant A. For this design, it's going to be 0.4. And then the other one is the radius of the atoms. Well, the atoms in specifically, most people use holes, and the parameter there is going to be the radius. So often with photonic crystals, you'll see the reference of R over A. And for this one, the R over A is 0.36. And the dielectric this crystal is in, I've given it a refractive index of 2.65, which is the white area on the crystal. And then the black area is the air holes that have been theoretically etched into this material. So a little more about the lattice, because we need to know a bit about it for when we're doing our design work. And one of the things we actually need to know is the horizontal height and the vertical of this lattice, because the lattices are defined in different ways. This particular one is defined using two vectors. The first one is the A vector, which has a vertical height of √3/2 times whatever your lattice constant is going to be, and a horizontal of 0.5 times your lattice constant. And the second vector is going to be vector C, which is 1 times the lattice constant. There is a third vector if you're working in 3D, which is labeled B in our product, but these are the two vectors we're going to use because we're going to be doing 2D simulations. So these quantities are important because what I'm going to do when I do my design is I will set these to parameters within the product, which I'll show you how I do this. And I'll use that. So I can, instead of saying 3 times this, I just say 3 times vertical height. So it simplifies your design work, and if you want to change your design. So I'm going to switch over to that product now. So this is the OptiFDTD designer. OptiFDTD comes in 2 products. There's the designer component and the analyzer component. This is the designer. What I've done here is I've created a space with a background of this WG example. It's the 2.65. And you'll notice in a lot of places, I don't have numbers, I have variables. So for example, my length is set to L and my width is set to W. If we come up to simulation and go to edit parameters, you'll see what parameters I'm working with. So I've got the dimensions for the domain. I also have these important parameters, the R over A, the A, and then I actually go ahead and calculate the R over A. So these are used throughout the design. But what I've done here is I've created a small crystal. I don't care about how big it is right now because we're going to be doing a band gap analysis on it. So for this, we only need 1 cell, which is just this one parallelogram down here on the bottom left. So I'm going to open up the crystal structure to show you how this gets set up. So this is the properties of the structure. First, we define that bottom left-hand corner, which is this one right here, which is currently set at 0, 0. We don't worry about depth or anything because this is a 2D simulation. And then we get into those properties where I commented on the A, the R over A, and the lattice. So this is where we define the lattice type. There's a number of different lattices that can be defined within the product. We're using the standard 2D hexagonal. And you'll see we have these vectors. The vector A, which I showed in the diagram, and then vector C, and we're ignoring B. And I've specified that this crystal is going to be 4 unit cells along the A vector. So we see 3 of them here and the start of the 4th at the top. And I have 4 unit cells along the C vector. So that's these 4 along here. The A, is that actual lattice constant. This is multiplied by these components to get the actual size of the lattice. So if I changed A, if I made it larger, this crystal would automatically modify itself. The atoms are edited over here on the top right. So right now we're using elliptical waveguides. So I'm going to open it up. And again, you'll see instead of specifying an actual number, I just put in the R, so that if I've changed my mind, I want to change my design, I just change R and I don't have to go through and change everything. And these particular atoms are given an air material profile so that we get the proper distribution. Now, we're not going to run an FDTD simulation. What we're going to do is a band gap analysis, which is a plane wave expansion method. So that's this form here. As I said, we're running 2D. This one, I'm interested in the TM band gap. We don't need to worry about the supercells. I'll show that in another example. The lattice vectors we just leave alone. And then this is your mesh. The mesh is the equivalent of discretization for other methods. You want to make sure that this delta is representative of your structure. So for example, the smallest structure we have in this are the holes themselves, which is 0.144. This 25 nanometers is good for that. The other thing you need to keep in mind also is these gaps. You need enough points along these gaps to define it. So in photonic crystals, one of the things people get caught up on is they look at the size of the hole for their meshing, but they don't think about how close those holes are to each other. So that's something to keep in mind. This default is good for this structure. And over here is details for the actual calculation. So we want 5 bands. I'll show you what those bands are in a second. And then the K vector path is the path in K space or momentum space that the product will use to do the calculations. We have it pre-programmed for hexagonal within the product. So you just select hexagonal and then we hit run. And what will happen is it'll run the band gap analysis and we will see the band structure, the optical band structure of this crystal. So each one of these lines is a band. So that's those 5 bands I mentioned earlier. And each one corresponds to a propagating mode through the structure. And you'll see that there's actually a gap. There is no mode supported in this region. So when I come back to the presentation, we'll talk about that gap. So when you look at band structures, this vertical axis changes depending on the different texts and references. Often it's showed as a normalized quantity. So you see A over lambda, A being your lattice constant, or omega A over 2 pi C. In that notation, this band gap is from 0.29 to 0.41. We present it without the normalization to the lattice constant. So that's why you say omega over 2 pi C, which corresponds to 1 over lambda, which is why there's the 1 over micron. That band gap corresponds to a wavelength of 0.97 to 1.35. So we're going to be interested in modes in that region when we add defects. As we add defects, we introduce the ability for modes to exist inside this band gap. And the question is, how do we go about sorting out where these modes are, what they are, how they look, and so on and so forth. This is where we take a look at that supercell behavior I was talking about earlier. So we come back to the design. I'm going to open up the same design, but this one has a defect. And the way we get defects is this button up here allows us to edit the lattice. And when you right click on a unit cell, you can either turn the cell on or turn it off. And you can also turn off groups. So you can edit your lattice that way. But we've got this defect. Everything here is the same as the previous design, except we're going to change up the plane wave expansion method approach. The difference here, you'll see there's fundamentally only two places where things have changed. So the first is the supercells. So what we say here, when we did our plane wave expansion in the first time, we only used one cell. A supercell analysis will run the same calculation, but it will run it over multiple cells. In this case, I'm specifying 3 cells along A and then 3 cells along C. So that will allow us to encapsulate the defect. You'll notice that because it's a supercell, this delta, even though there's 16 points, same as before, the delta is larger because it's covering a larger distance. It's covering 3 unit cells along that direction. That's still a fine enough resolution for now. If you were doing this for a paper, for example, you'd want to do convergence tests and make sure it doesn't change. But for this purposes, it's good. The other thing that we're going to change is instead of 5 bands, we're going to add 30 because the band structure for a supercell is a lot more complicated. And you'll end up needing more bands to describe things. So I'm going to run this. It's going to save the design. And we will see the structure, and you can see what I mean by it being more complicated. There is more bands that have been introduced. But what's important to notice is in that same region, so right around here, where this is where we had the band gap before, we have these 2 almost horizontal lines. Those are defect modes. Those are modes that have been introduced by the defect. So we're going to take a look at those in a second, and I'm going to go back to the presentation. So if you take a look at the values of those, you use the tracer functionality in the product, you find out that those modes correspond to 1.17 to 1.26, depending on whether you're selecting it over here or over here. So we know there's going to be a mode around kind of 1.2-ish region. So that's more information we're going to use. Before I get into the full analysis of this structure, running an FDTD simulation and everything, I want to talk about Q-factor analysis because that is one of the big things you do on a mode. So Q-factor is a measure of how good the cavity is, how well it retains energy. And depending on your application, this is important information for you. So coming over to Q-factor analysis. The traditional definition of it, the standard definition of it, is it's the ratio of the resonant frequency of the cavity relative to the spectral full width half max bandwidth of that cavity. So what I mean by that is if I take a look at the time domain information for that cavity, I do a Fourier transform on it, I get the spectrum, I measure the peak, and then I measure the bandwidth, and the Q is the ratio of those two things. Here's the problem with that though. With photonic crystal cavities, if you engineer them carefully, they can get very high, which means they hold the information there for a very long time, which means you need to run your simulation for many, 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 many time steps, because otherwise you're just not getting enough information about the decay because the decay is so low. This is obviously a problem in FDTD simulations, which are computationally intensive. And running them long enough for something with a Q factor of 1,000 is just not feasible. So there is another way of calculating the Q factor, and I refer to it as decay analysis. This is based on the form the electric field takes near a resonance, as reported by Novotny and Hecht. So we see here the expression for the electric field. It's this exponential in terms of the resonant frequency and the Q factor. If we linearize that by taking the log, we can actually equate this to the slope of that log decay. And then we can rewrite the expression for Q in terms of resonant frequency and the slope of the decay. So we can do some post-processing on the time domain information, we can get the slope, and then we can just do this calculation. I'm going to show how to do it both ways within the product and with external post-processing. So the first example we have here is the one I've already mentioned, with the R over A of 0.36, A of 0.4 microns, and the refractive index at 2.65. We already have the defect. This is a single defect, so one hole has been removed. And now I'm going to show you the design of this crystal within the product. So this is that crystal. You'll see that I've truncated. So if I select the crystal, I've truncated some of the cells that are outside of the domain. It's just to make things aesthetically pleasing. It has no bearing on the simulation if it's outside of the domain. What we have here is a number of things. We have the crystal, which we had in our previous example, but in this one, we now have sources and observers for setting up the simulation and for recording that information. So first, I'm going to talk about the crystal structure. So this is the same as what we saw before. Everything's in terms of R and A. The difference here that I did want to show is I also want these parameters. Instead of just setting the position at 0, 0 up here, I wanted it down here, and I wanted to position it such that the defect was at the center of my domain. The way I was able to do that was a calculation involving L over 2, which is the length of I by 2, and using this H vect. So if we take a look at the parameters, we have a V vect, vertical vector, and H vect. That's those quantities I showed you when we talked about the lattice. So I was able to set up a convenient equation to be able to do this, to design this crystal. Otherwise, this crystal is exactly the same as the previous one. The point source is located at the center, L over 2, and everything else is pretty much default. Normally, this defaults to a continuous wave. We want many frequencies. We want to look at the spectrum, so we're going to run a pulsed simulation. So it's a sine wave modulated by a Gaussian. And we're going to set the central wavelength to about 0.9. I don't really want the wavelength to be right on top of my mode, which we expect to be at about 1.2, but I want it close enough. And if we take a look at the pulse properties, this is what the pulse is going to look like in time, and this is what it looks like in frequency space. You can play with these quantities to get a broader spectrum, but generally the default value is more than enough. It's fine for us for this case. And if I go to the observation point, you'll notice the observation point is not located dead on center. I've located it a bit off of center. I don't want it directly picking up the source. So it's located just a bit offset from center, and I have it set up to record all three components in TM plus the pointing vectors. The observation area is purely to show us what the mode looks like. So it's centered on the design, and I gave it a length and width of 2 microns. The observation areas can be used for a number of things, but for the purposes of this, it was just to visually show you what the modes look like. The thing to keep in mind is the larger your observation area, the more data the product is calculating, the slower your simulation will be. So that's everything for the design work on this crystal. I want to talk about the FDTD simulation we're going to run now. There's a couple things you want to keep in mind. One is the mesh. The auto setting is designed, it takes a look at the source, and it takes a look at the refractive index, and it calculates what it thinks would be good. It's lambda by 10 in the highest material. That's normally okay for a ballpark thing. However, it does not take into consideration the structure. So for example, these holes are 0.144 microns in radius. So they're only 0.2 microns across, which means there's only 6 points across one of those. No, more than 2. Yeah, there's not enough. Mental math on the spot's a bit of an issue there. So typically what you'll do is you'll take an initial guess on what your mesh should be based on your structure. And then what you'll do is you will run convergence testing. You'll run your simulation, look at your results, make your mesh smaller, run your simulation again, confirm. and you're going to get to a point where changing the mesh doesn't change the results, and that's converged. You typically don't want to touch the time step size. This is based on the courant stability condition, so don't touch it. And then if we go to this one here, which is the number of time steps, you want to make sure this is long enough so that you're getting enough information. If the auto setting is only to get the field from one corner to another corner, in resonance structures, that's not enough. So in this case, I'm running it for 50,000. And at this point, I would then run it. I've already run that, so which is this structure here. So we're going to take a look at the observation point. So this is the field information for the HY for that field. So we can see that it does decay down, and then there's this gradual decay. If we take a look at the frequency of this thing, and I'm going to set my a bit broader so we can show this, we can see a number of spikes corresponding to modes. Now, this one here on the left, this tall one, and this one here on the right, these correspond to the band edges. So right on the edge of your band gap, you'll get modes. Those we don't care about. The one we care about is this one right here in the center. And this one, we're going to increase our resolution. So we're going to zoom this down. So we're going to look at 1.13 and 1.3, no, 1.21. Hit OK. So now we've zoomed in on it a bit more. Well, we've recalculated to closer values. And what we're going to do is we would calculate the peak on this. I'll do that now, actually. Actually, we're going to use tracer. So if we take a look at this, we see that this mode is at 1.19 microns, which is exactly where we expected it to be. So if we come over to our observation area and we look at 1.1, as close to 1.19 as we can get, we can see this is a, well, this is a bit off, this wavelength is a bit off. We can see we have, I look at the pointing vector. So if we look at our pointing vector, we see a very highly confined mode, which is what we're going to be looking at. So if we come back, we're going to do our analysis on this. What you're going to do is you're going to switch to frequency, and then we're going to create markers at the peak and then at the two halfway points. So I'm going to come back to the slide deck where I've captured that. And what we see here is we have our peak at 250 terahertz. We have this bandwidth, which is 1.3 terahertz. And then we get a Q factor of 191.647. So that's how you would traditionally do this, by taking a look at the spectral response. The next step would be to take a look at this decay analysis. And the way that's done is we would export this field. So if we go back to our analyzer product, we go back to this time domain, we would export this to a data file. And then we could have done this through VB script, or because of the extra processing I did in Python, I'm going to post-process this structure. So I'm going to show you the Python script. I can make this available to people who are interested. So what this script does is it reads in the data file, which is this information here. Then what it does is it truncates the noise at the beginning of it that's due to the source. And then what we do is we take the log of it. We take a look at only the peaks to try and smooth out and figure out the envelope. And then we do a linear regression to get the slope, which allows us to do our Q calculation. So if we go back to the slide deck, you'll see the results from that. So here was the time domain information in the top left. Then we take the log of it, which is this one here on the top right, the log of the square of it. My apologies. That should say log right there. And this one down on the bottom is just these peaks plotted. And you can see it's smoothed it out. And when we do our linear regression, we get our slope. And then putting that with the resonant frequency from before into this, we can calculate our Q factor, which is 176. So the decay got 176. The spectrum gave us 191. If we had to run this simulation for longer, the spectrum calculation would have gotten more accurate and dropped. And the other way of making this more accurate is, as you saw, we had other modes in there that are contributing to this time information. One of the ways to do this would have been to have filtered it out for just this mode. So what you would have done is you would have taken your time domain information, converted it over to a spectrum, applied a filter, which just captured that mode, then put it back to time domain and done this calculation. In which case, it would have improved the decay calculation, and these would have gotten even closer. They're at about 8% difference right now. I'm going to very briefly look at a second design. It's the same work. There's just a couple things I want to show you with this in the time we have. So this particular one has an R over A of 0.34. It has a different effective index. It's 2.33. And the lattice constant is slightly different. It's 0.41. The other thing to notice is this has 3 holes that have been removed. It's a different cavity design. So we're going to go back to the designer. And we'll see this is a slightly different structure. So in the previous one, I set the background of the domain to be my dielectric. In this one, the background is set to air. And this material, the dielectric, is set as a waveguide, and it just fills the space with the material. So it's a slightly different way of doing it, but it's the same concept. I fill the space with material, and then I drill etch air holes into it. So this particular one is a bit simpler in terms of the parameters. It only has the R and the A. It doesn't do any other calculations. So if you wanted to change your R over A, you'd have to do that manually. And this one doesn't have those H vectors and V vectors calculated. So it actually, if we go into the crystal structure, it does those manual calculations. So there's your square root of 3 over 2 for the vertical multiplied by A. So different ways of doing it. So this is a slightly different way of doing it. Everything else is pretty much the same on this one. This one uses a wavelength of 1.1 for its source, the central wavelength of the source. And then that's it for this design. I did shift the point source off a bit for this one because it was required for the mode that I'm after. One of the things when you're first exploring these that's useful is to create a few observation points, because you'll find that based on the mode you're looking for, one of the observation points might be better placed than another. For example, putting it right at the center for a dipole isn't very useful because there's no field at the center, or very little field at the center. So if we switch over after running the analysis on that, the crystal, the FDTD simulation, we get these results. So again, we're going to take a look at the observation point. This is the information we have on this one. So if we switch it to frequency domain, and again, I'm going to, whoops, we're still in frequency. I want to put this in wavelength. So make this a bit broader so I can show you guys the full band, full mode thing. And again, what we'll see is we'll see a bunch of modes, or not modes, but field out on the edges of the spectrum. We'll see 2 sharp peaks. These correspond to the band edges. And then you'll see this giant mode right in the center. So I'm going to narrow down on that mode, 1.1 to 1.2. So this is that mode that we were looking at. And as with the previous example, we would use our marker. You go back to your frequency. You put your markers, you're going to create one of the resonant, and then you're going to create to get your bandwidth. So if we come back to the slide deck, I was a little more cautious and I got it for us. So this one came out with a Q factor of 394.944. So that's the Q factor for this structure based on the spectral analysis. And the decay, again, we exported the decay in the time domain information. We put it through the script. We see this one actually came out much cleaner than the other one. This one, there was really only that one mode that was present. And then when we run that through the script, we get a Q factor of 387.276. Again, this could have been improved by running the spectrum longer. This particular simulation was run 100,000 points instead of the 50,000 of the first one. So it's a bit more accurate. And we could have done some filtering. As I said, this one doesn't need this particular one doesn't need the filtering the same way. So that wouldn't improve the results as much. But what we do see here is it's improved by about 2%. So they give comparable results. And what you'll find if you started, say, at 10,000, simulation of 10,000 steps, 20,000 steps, 30,000 steps, 40,000, so on and so forth, you do a convergence on the number of time steps. What you would find is that the decay analysis will give you the converged result faster than the spectrum will, which is useful. That is the wrap up of the two designs I wanted to talk about and some of the analysis that we can do within the product and using external scripts. As I said, whenever you're doing a post-processing, you can either use a VB script within the product, which I can show. We have a number of webinars that do VB script analysis. This particular one, because of some of the peak finding algorithms, I wanted to use Python so I could use the standard libraries that everybody was familiar with. So that's that there. So now what I'd like to do is I see there's a number of questions that are there. I'd like to go ahead and start taking a look at them now. So the first one I have here is from Alec. What's the advantage over hexagonal over square lattice structure? The band gaps are different. So the locations of them are different and the nature of them are different. So a hexagonal lattice, if you choose the correct R over A value, will give you what's called the complete band gap. It will give you a band gap in both the TE and the TM polarizations. Square lattice can't do that. You can get band gaps in TE and you can get band gaps in TM, but they both require different different sizing of the atoms and the lattice constant. So the hexagonal lattice, if you choose an R over A of 0.48, it brings the holes very close to each other. It's more like veins. That will give you a complete band gap. And that is one of the reasons why the hexagonal structure is often preferred. It's the default 2D structure. The next question we've got here is, under what circumstances would a researcher use one of the Q factor calculations over the other one? So for example, as I said before, the spectrum one is the standard definition and it's the one people used to use the most. The problem with it is the mode needs to decay enough for you to capture that information within the spectrum information, right? Because your mode, as it decays, your mode is going to become more and more of a Lorentzian. And you need it to be at that state to get the correct information for the spectrum analysis. The decay analysis doesn't require that information. So long as you have enough of the decay to calculate the slope, you can calculate it. So the decay analysis is a bit of a roundabout way of calculating it, but if you've got a high Q, so these structures, I was easily able to get the spectrum information with 50,000 or 100,000 steps. But if they only had a couple hundred Q factor. Now, if you had a Q factor of 10,000, you wouldn't want to run that simulation to do the spectrum analysis. You would want to use the analysis. The decay analysis. So one of the things here, the discretization. I could do an entire webinar on just discretization, actually. The results are sensitive to discretization resolutions. which is why with any FDTD product and any FDTD design, you're going to want to do convergence testing. You get your results at a mesh resolution of 0.1, go ahead and run your simulation with a mesh resolution of 0.05, then run it with 0.025. And you're going to keep doing that and looking at results. You will hit a point where increasing the resolution will not change the results. So that's where that sensitivity to discretization is. So I have,
if you want to, oh, sorry. I was just going to say, if you want to scroll down to the bottom, there's a ton of new questions coming in as well.
Okay. Yeah, I was just starting at the top and working my way down.
Okay.
So 2D versus 3D. Yes, I was doing 2D simulations versus 3D structures. So one of the tricks that gets done, at least for your initial analysis, is those refractive index values I used for the dielectric weren't the refractive index of the actual dielectric that would be used for the structure. They would be the effective indexes. So you take a look at your structure, it's got air, then it's got silicon, then it's got silicon dioxide, and then it's got silicon again. You do a modal analysis on the vertical to figure out what the effective index is. Then you use that effective index for your calculation. It's kind of like a 2.5D simulation. They can be in the ballpark, but if you're looking to nail it down, I would recommend running 3D simulations. So you would want to define the thickness and run a 3D FDTD simulation. This was one that I see here. The R over A value for I mentioned the complete band gap. So R over A should be 0.48 for complete band gap. I didn't use that. The reason I didn't use that is it brings the holes really close together and you have to run very high resolutions. And if I was going to run simulations during the webinar, that wouldn't have been feasible. So I didn't want to do that. I'm just scrolling down here. Yes, sorry. From Gabby, there's a question here about whether you can position the source at different points in the photonic structure. You absolutely can. I wouldn't necessarily, I wouldn't use a point source in that case. If you were looking at propagation, Gabby's asking about boundaries. If you were looking at perhaps propagation through the structure, I would set up a input plane outside of the domain and run it. But yeah, you can put the source wherever you want. It just depends on what information you're looking to get out of there. Pradeep is asking about whether the calculation is valid for dielectric cylinders versus spheres. Photonic crystals, you're etching a cylinder into a membrane. You're etching a hole into the membrane. So that is the most valid approach for the design. This calculation would work with spheres as well, but you'd have to be running a 3D simulation because those are 3D structures. I've got a couple of questions, Gabby, as well as a couple others comment on simulation duration. Fundamentally, it's difficult to say how long the simulation takes because it's going to very much depend on the resolution you require for running that simulation and the size of it. So it's not the fact that we're running the source from the cavity center that's dictating the simulation needing to run for a long time. It's the fact that there is a cavity. So you want to run the simulation long enough so that you're getting enough information in there. So that's a bit of I know it's a bit of a wishy-washy answer, but it does highly vary depending on the designs. Sorry, I'm just reading through some of these. I do have a couple questions here about acoustic resonance. The OptiFDTD product is an optical modeler, so it doesn't have the equations for calculating the acoustic. There's a couple people here asking about the relevance of photonic crystal research. It's still I don't know if I'd call it growing in the way it was in the early 2000s, but it's still very much a hot area for research. It's moved. There's probably more focus in photonic crystal fibers than there is in planar photonic crystals these days. There's still significant research in photonic crystal planar structures, but if you're looking for the hot topic, it's definitely multi-mode in multi-core fibers and photonic crystal fibers. We have a number of webinars through the site that we ran using the OptiMode product in conjunction with the OptiSystem product, looking at doing photonic crystal fibers in systems. So yeah, photonic crystal research is still very much a thing. I've got a couple questions here about parametric sweeps. So parametric sweeps can be done in two different ways. One of them is an actual, actually I can show it in the, let me bring up the product, designer. So you can actually do a parameter sweep. If I go to simulation and click on parameter sweep, you actually select the parameters you want to do your sweep on. So let's say you want to change your R value, and then we can actually sweep that value and it'll run the simulations. The other way of doing it would be a script. You can run a VB script that will actually do the sweep for you as well. 3D photonic crystals, that's going to depend a little bit on what you mean by 3D photonic crystal. Do you mean, sorry, this is from Gustavo. 3D photonic crystal depends on whether you're talking about 3D photonic crystal like woodpile structures. Those would need to be built. We do have some of those built within the photonic crystal product. But for this, if you wanted to model this 2D crystal as a 3D structure, this particular one actually already is. So you see that we have the membrane layer, and then we have the air holes etched. Soybaum has asked about the light line. The band structure product does not include the calculation for the light line. So that's that. From Romana, in terms of significance to solar cells, so Romana is asking about bearing of this on solar cells. This particular webinar, not so much because it's a cavity design, but one of the growing areas where a lot of photonic crystal folks are getting into is into particularly things like the back reflectors for solar cells. So there's some relevance in terms of the structure design, but not so much in the cavity analysis. Sorry, I'm just scrolling through here to see what we've got. I'm still getting a couple folks asking about when you would use the decay analysis versus the spectrum analysis. Typically, you would default to using the spectrum analysis, but if you find the Q factor is too high for you to get reliable results, you would default back to the decay analysis. Somebody's asking about work with a training package for OptiWave. I'm not sure if you're asking about this particular webinar or if you're asking for training sessions from the company. If you're looking for training sessions or other training packages, I would contact support at optiwave.com, and we can follow up specifically on your concerns there. I've got a question here from Arturo asking if it's possible to set the direction of propagation perpendicular to the lattice vectors. I'm assuming you mean that in terms of the comments I was making about the polarization to make them match other products. That can't be done, but if you're asking about being able to, for example, propagate along, like normally with a photon crystal, you're propagating in the XZ, but if you wanted to be able to propagate along the Y, that is possible with the most recent version of the product. We do have Y propagation, so that can be modeled. In terms of, and the last remaining question I've got here is the difference between our software and other commercial software. Oh, sorry, there is another question I'd like to address after this one. It's an FDTD engine. So at their very core, FDTD engines are all basically operating on the same algorithm. The question, it comes down to user interface, post-processing functionality, and different optimizations. Different products will handle the materials differently. So depending on your application, one product might run mildly faster than another one. That's about the best I can do on answering that, because it's going to depend on the specific application, and I don't want to get into that here. The other question that I'm going to take a look at is there is a question about GPU computing. We do not support GPU computing at this time. One of the problems is you very quickly get into situations where the overhead of managing all the cells in a GPU computing environment for FDTD, it offsets the advantage. One thing, if you're looking at doing larger simulations, is that FDTD, our FDTD product, is supported by the Amazon cloud environment. So what we do is we have a platform where you can upload your design. You generate your design on your desktop. You can upload the design, and the platform will help you select the instance, set up the funding for that instance, and then run it. And once the simulation is done, it will close it for you. So if you're looking for heavy computing power for a particularly high resolution design or a larger design, that's typically the spot we would direct folks. That's, I'm just scrolling to see if anything else. Yeah, there's just one question here, again, in regards to the TE and TM. So go back, when the video comes out, go back and look at the start of it. FDTD, the OptiFDTD product reports, if you calculate a TE band gap, it will be a TM band gap in molding the flow of light, if that's the reference you're looking at. If you calculate a TM, it matches the band gap in the TE in molding the flow of light. And it's because of that definition that I talked about at the beginning of the webinar in regards to your coordinates and how you define transverse. We use a standard set out by the waveguide researchers. You can find that Okamoto is probably the best reference I use for waveguides in that. And then the other standard would be the one in molding the flow of light. I believe that wraps it up for the questions. I'll hand it back.
Thanks so much, Scott, and thank you, OptiWave, for sponsoring today's webinar. There were a ton of questions, so if you all still have any questions or have any follow-up questions to the answers Scott gave, you're more than welcome to contact them directly. And Scott, if you wouldn't mind, maybe in the chat box, you could send everyone your email address or an email address that they can contact in case they have any outstanding questions from this webinar or post-webinar after watching the recording. But thank you again all for joining, and thank you for participating, and we will see you all at the next event.